Hello.
Can you see my screen?
Uh,
Hello?
yes,
Can you
yes,
see?
yes,
Okay,
yes. I,
great.
I can see your screen.
Yeah, so just full screen it. Yeah. Now you can also see, right?
Yes, I can see. You can go to the next page of.
Okay,
Yes, yes. It's working. It's working.
perfect. Yeah. So thank you for the invitation. Yeah.
Let's wait for a few minutes and then let people join. People generally join a little bit late, so let's wait for
Sure.
a few minutes.
So 45 minutes, right?
Yes, 45 minutes.
Mm.
Okay, so I think we can start. Okay.
Mm.
Okay, so welcome everyone to today's Majorana-Raychaudhuri seminar. So today we have Qianhang DING from IBS, and he will be talking about primordial black hole mergers as a cosmological proof. Qianhang, you can start.
Yeah, thank you for the introduction. So also it's my great pleasure to to give a talk in the Majorana-Raychaudhuri seminar. So basically, I'm going to talk about how to use the primordial black hole mergers as a cosmological probe. So this talk is based on these two work with Mingxi He, also from IBS, and Vladimir Takhikovsky from the QUP in KK. Uh, uh, so this is the historical evolution of our universe. In order to understand our universe, we need to probe our universe. So, in order to fully understand our universe, we at least should probe our universe at two levels. One is on the background level, which is corresponding with the Hubble expansion rate, how our universe is expand. And the second one is at the forethought level, that is how the density fluctuation slowly form the structure, which is about the structure formation. Therefore, in the first part, we'll mainly talk about the background level, the Hubble expansion rate. Uh, so so currently, about Hubble expansion rate, the Hubble parameter, we already have a lot of methods to measure it. For example, in the early universe, we have the CMB, cosmic microwave background, which can measure the Hubble expansion rate, uh, given a value around 67.4 kilometer per second per microsecond. And this is the early universe measurement method at redshift 1000. And in the later universe, we also have some other methods, for example, like type Ia supernova or Cepheid variable. This kind of standard candle, we can also measure it at low redshift, which is give a value around 73.04 kilometer per second per second. You can find these two values do not match with each other and have a phi sigma inconsistency. So this is well-known Hubble tension. And also, in order to understand where does the Hubble tension come from, we need to develop other method to independently measure the Hubble parameter. Therefore, we also have some other methods like at large scale structure, we have the BAO peak. This BAO peak can help us to measure. And since 2015, we first observed gravitational wave from binary black hole. And the binary black hole can be another independent method to measure the Hubble parameter, but still in a relatively small, still at the redshift smaller than 10. So in such a case, so how can we measure the Hubble parameter independently in an intermediate redshift range? For example, in the dark age, so in the dark age, we don't have much astrophysical object to help us to measure the cosmic expansion rate. So how can we do it? For example, some very specific theoretical hypothetical object like Primordial black hole can be a potential candidate. The reason is the Primordial black hole was born at very early universe, and if their mass is larger than the 10 to 15 gram, they can exist until now. Therefore, the Primordial black hole exists at such a very high redshift around, and their signal can be a potential observable to help us to measure the Hubble parameter. So, which kind of signal from Primordial black hole? Since such a very high redshift is corresponding with a very large cosmological distance, the signal will decay very strongly. Therefore, a very important signal, that is a gravitational wave from the binary Primordial black hole, will be very important. So for Primordial black hole, their gravitational wave, it has a waveform like this kind of form. And from the gravitational waveform, we can extract some key quantity, like from the gravitational wave phase. From the phase evolution, we can obtain the redshifted mass of the Primordial black hole binary. And this redshifted mass of the Primordial binary is the combination of the intrinsic mass of Primordial black hole binary with their corresponding cosmic redshift. And we apply this redshifted mass into the amplitude of this gravitational waveform. We can here, and we can obtain the luminosity distance between this PBH binary and us. And this is the luminosity distance. And you can find it depends on the Hubble parameter value here, and also depends on the cosmic redshift. And this depends on the cosmological model here. We use the lambda CDM model as a benchmark model here to apply here. Therefore, here you can find in all the luminosity distance is observable, and the Hubble parameter value is the quantity we want to get. But we don't know the redshift since the redshift is hidden in this redshifted mass. It's a combination with intrinsic mass. Therefore, in order to obtain this Hubble parameter, we need to know a relation between the luminosity distance and the redshift. And since the redshift is encoded in the redshifted mass, therefore, we need to extract the redshift information from this redshifted mass. How can we do it? So the key point is to construct a redshift distance relation. And to do so, very important properties for PBH is very key, is key point. That is a statistical property of PBH. So which kind of statistical properties like, for example, when PBH was formed from the primordial quantum fluctuation when it's go outside the horizon and re-enter the horizon from the PBH. And the PBH follow a unique mass function, mass distribution. For example, in the inflationary formation, PBH formation scenario, PBH always follows such a log-normal type mass function. So, and in the other formation formalism, they may form some power law forms mass function, but no matter in which kind of formation mechanism, they always follow. They always has a unique mass function. So, as we introduced, since 2015, we observe gravitational wave and we can obtain their redshift mass and corresponding luminosity distance. To obtain this Hubble parameter value, we need to know this redshift. Therefore, we need to use the PBH mass function to obtain this redshift. So how to do so? So for example, in the future, like gravitational wave detector like LISA, like Einstein telescope, they can detect the binary black hole event up to the redshift 100 to 1000. So if we observe a gravitational wave from binary black hole from the redshift larger than 20, that means this kind of black hole must form at redshift larger than 20. However, for astrophysical black holes, they form only small. Their formation is smaller than the redshift 20. Therefore, if we can use such an Einstein telescope or LISA to detect some binary black hole larger than redshift 20, that they must be the primordial black hole binary. And if in the future we observe a number of primordial black hole binaries, and for each primordial black hole binary, they have a redshifted mass and corresponding with a luminosity distance. Here, in this luminosity distance, we need to know this Hubble parameter, but we don't know the redshift as we introduced. However, what we know is the Hubble parameter is an independent value, independent on the PBH, independent on the redshift. Hubble parameter value should be a constant. Therefore, we can assume a value of Hubble parameter as anyone. For example, 80. We assume a value of Hubble parameter and apply it in this equation. And this luminosity distance is observed quantity. Combined with the assumed value of Hubble parameter, we can solve this corresponding redshift. Therefore, for each observed luminosity for each PBH binary, and combined with the assumed value of Hubble parameter, we can solve a redshift. And we apply this redshift in this observed redshifted mass, we can obtain the intrinsic mass of a PBH. If in the future we observe a probability distribution of redshift mass of PBH like this, and we assume a value of Hubble parameter, use such a process, we can obtain an intrinsic mass distribution of PBH. You can find this actually this intrinsic mass distribution depends on the assumed value of Hubble parameter. Therefore, if we can theoretically or observationally know the physical PBH mass function and to compare it with this Hubble parameter dependent mass function to fit it, then this kind of method can tell us what's the physical value of Hubble parameter. So in order to really do it, we need to first to build a relation between this probability distribution with the PBH probability distribution of the redshift mass with the PBH mass function. So how to do it? So we first, in order to calculate the probability distribution, we first need to calculate the cumulative distribution. The cumulative distribution is defined as if we want to know the cumulative distribution at this this coordinate, is defined as the number of PBH bandwidth with their redshifted mass smaller than these two quantities divided over the total PBH bandwidth number. And this cumulative distribution can be calculated via a triple integration over the PBH mass function here. And this PBH NM1, NM2, this multiplication means determines the probability for two PBH with intrinsic mass M1 and M2. And also, we not only need the PBH binary with these two intrinsic mass, we also need then they can be detected by a gravitational wave detector. So here we need to multiply with a gravitational detector determined detectable window function, which determine how many PBH binary with these two intrinsic mass can be detected. And also, for PBH binary with these two intrinsic mass, if they are located at different redshift, the observed redshift mass are differently. Therefore, here we need to multiply with a redshift distribution of PBH binaries, and we do such a triple integration, we can obtain such a cumulative distribution. And then we need to obtain the probability distribution on this two redshift mass. In order to do so, we need to do derivative on this cumulative distribution on two redshift mass. And we already have the cumulative distribution, and we do derivative on it, we can obtain such a relation. Here we can obtain a relation between the observed probability distribution of redshift mass with PBH mass function here. But here we still have two quantities. One is what is the detectable window function. Another one is what is the redshift distribution of PBH boundary. We don't know it. We need to first to know them. So for the detectable window function, that is for a given gravitational wave detector. For example, here we choose BBO as a benchmark detector. How to calculate it? The calculation is is defined as the observed PBH bandwidth over the total PBH bandwidth for a given PBH bandwidth intrinsic mass at a redshift. And in order to calculate it, we need to calculate the orbital parameter distribution over the semi-major axis and eccentricity at the redshift z, and to integrate it over the detectable semi-major axis and eccentricity. And how to know this detectable semi-major axis and eccentricity? We need to calculate the gravitational wave signal to noise ratio. They must be larger than a threshold value. For example, for LIGO, we always choose 8 as a threshold value to say this boundary can be detected, and we apply it in this integration. Then it can give us this window function. And for this redshift, the PBH boundary redshift distribution, here we first use the PBH boundary merge rate as a benchmark model to calculate it. So now we already have the window function, and we already have the redshift distribution, and we also have the relation between probability distribution and PBH mass function. Therefore, here you can find. For example, here we use the PBH log normal type mass function as an example. You can find their probability distribution on two redshift mass looks like this kind of distribution. And also, if we choose this power law PBH mass function and their redshift mass distribution like this, so you can find this two redshift mass probability distribution behaves differently. Therefore, such a distribution can, in principle, as observable to determine the PBH mass function. But how? How to, if in the future we really observe such a distribution, how to use this distribution to determine the PBH mass function? The key, therefore, this is observable. This is a relation. How to form this observable using this relation to determine this PBH mass function? So this is actually an integral equation. It's very difficult to solve. But nowadays, we have a very fancy, for example, we have the machine learning method. The AI is very popular in physics. And in machine learning, there is a very important method called the gradient descent method. And this method can help us to obtain the PBH physical mass function from this observable. How to do it? For example, the observable probability distribution is corresponding with a PBH physical mass function. and we don't know this physical mass function, but we can guess, we can randomly guess the PBH mass function, and we label it as n tilde, n prime. And of course, we guess the PBH mass function is not correct, but we can do a calculation to integrate this equation, and we can obtain a theoretical probability distribution from this guessed PBH mass function. Of course, the theoretical guess the distribution is not equal. They do not equal this observed distribution. Therefore, there must be some difference between them. So we can estimate their difference. So we calculate the difference between the theoretical probability distribution with observational distribution, and we call this as an error function. When the theoretical distribution does not equal the observational distribution, the error function is a positive value, and only when we guess the correct, we obtain correct the PBH mass function, the theoretical distribution equal observational distribution, this error function equals 0. So our purpose to upgrade our guess the PBH mass function is to keep decreasing the value of error function. So we calculate the derivative of error function over the change of PBH mass function, and using it to keep upgrading our guessed PBH mass function to obtain a next guessed PBH mass function to keep decreasing this error function. So this is our basic algorithm. So let's see how this algorithm behaves in this equation, in this problem. So for example, here we have a PBH mass function. Here I choose a log-normal type mass function as example. And I don't know the physical mass function, but here I can randomly give an initial PBH mass function as example. Here you can find here. And then we just using this gradient descent method to run it, and you can find with this algorithm running and our guessed PBH mass function keep approaching to the physical mass function to its physical value, and it behaves very nicely. And then you can find the final result, the difference between our numerically calculated PBH mass function with this theoretical value. The error is smaller than 1%, so it behaves nicely, but this requires we must have a very nice observation on the PBH probability distribution. So based on this algorithm, we can from a given a probability distribution, we can obtain its corresponding PBH mass function. But in that relation, we actually don't know the PBH binary redshift distribution. Previously, we just used the PBH merge rate redshift distribution as a benchmark model to calculate, but actually we don't know it. We need to know it from the observation. So how to know this redshift distribution? So for example, so for each PBH binary, we can know their luminosity distance, and it's corresponding with Hubble parameter and redshift. And in order to construct this redshift distribution, we must know this redshift. Therefore, here we just assume a value of Hubble parameter like 80 or 70 or 60. We apply it here, and therefore this redshift can be solved from this luminosity distance and assume that value of Hubble parameter for one PBH binary, and we do such a calculation for all the PBH binaries we observed. Then we can observe the redshift distribution, but this redshift distribution is a distribution depends on assumed value of Hubble parameter, and therefore for observation we know this merge redshift mass distribution probability distribution, and also we assume a Hubble parameter value, obtain this redshifted distribution, and using this equation we can use gradient descent method to solve this PBH mass function. Of course, this mass function depends on this redshift distribution and depends on this assumed value of Hubble parameter. Therefore, we can find like if we assume different value of Hubble parameter, this is our obtained PBH mass function. You can find for different assumed value of Hubble parameter, they behave differently. So if in the future, theoretically or observationally, we can know the PBH mass function and compare with this Hubble parameter dependent mass function. It can help us to determine what is the true value of Hubble parameter. However, currently, we do not know the PBH mass function, so this is the bad news. But in the future, maybe we will have some method. But some observable is actually depends on the PBH mass function. For example, the PBH merge rate distribution is observable, which we can observe in the future gravitational wave detector, and their distribution can help us. It's related with the PBH mass function. So, for example, we can based on different PBH mass function, we can calculate the PBH merge rate distribution. And since if we want to from the probability distribution of PBH redshift mass, we want to use a gradient descent method to obtain the PBH mass function. This PBH mass function is a function depends on the Hubble parameter value, and therefore for different assumed value of Hubble parameter, our obtained PBH merge rate must depends on the Hubble parameter. And here you can find for different assumed Hubble parameter value, we can obtain the different behaves like a merge rate distribution. Therefore, PBH distribution is the observed value. So therefore, we can compare them and to obtain the true value of PBH mass function. So this is basically how we use the PBH binary merge rate distribution as a method to probe the Hubble expansion rate, and their result may tell us what's the true value of Hubble parameter from the in this such a high redshift range, and we can compare it with the CMB observed measured value and compare it with the Type Ia supernova measured value to help us to understand where is Hubble tension come from, and to know what is the true background physics and under the behind the Hubble tension. So this is the first part I want to discuss. So the second part I want to discuss is about how we use primordial black hole merge to study the structure formation to probe our universe at the first order level. So, in order to understand the structure formation in the late universe, what we need to study is how the dark matter is collapsed around to form the dark matter halo, and the baryon and the galaxy will form inside inside dark matter halo. Yeah, so this is based on this work. So, but then how we use the primordial black hole to probe the structure formation? That is, when the dark matter halo forms, the dark matter density inside dark matter halo is very dense, and PBH as a dark matter candidate inside such a dark matter dense range, their merge rate will be enhanced. And if the PBH merge rate is enhanced, this will significantly modify the PBH merge rate redshift evolution. Therefore, from the future gravitational wave detector, we measure its corresponding redshift evolution, PBH merge rate redshift evolution. It can help us to study the structure formation. So let's first take a look at some quantity to know how the dark matter distributed. For example, currently at the current universe, the average dark matter density is around 10 to minus 27 kilometer per cubic meter. However, inside our dark matter halo, for example, around our Milky Way, for the dark matter density around our solar system, the dark matter density is around 5 order larger than the average dark matter density in the current universe. So it's 5 order larger. So and also for dark matter halo is for the dark matter halo density profile follow the standard NFW profile. So if we get closer to the dark matter halo center, to the galaxy center, the dark matter density will increase a lot. And inside the galaxy center, what we have? We have a supermassive black hole. So around the supermassive black hole, And since the very strong gravitational attraction around supermassive black hole, the dark matter density will be strongly enhanced. And we just introduced the dark matter halo profile follows such an NFW profile. But since a very strong gravitational attraction around the supermassive black hole, there will be very special structure form around supermassive black hole, which is so-called the dark matter spike. And this dark matter spike will strongly enhance the dark matter density. And if PBH located around inside this dark matter spike, very dense PBH density will cause their merge rate strongly enhanced, and this enhanced merge rate will modify PBH merge rate in the redshift space. So this can help us to know how the dark matter is distributed and how the structure form. So let's say first about the dark matter spike. The dark matter spike was proposed around maybe almost 20 to 30 years ago by Joseph Silk and Dongnu Ganglu. So its basic idea is to solve the four-Planck equation in the strong gravitational potential around the supermassive black hole, and it will give us such a dark matter spike density profile. So you can compare it. Here, there is a very important quantity that is gamma. This gamma gamma spike is to describe the power index of the dark matter spike, and is related with this gamma. And this gamma is the dark matter halo power index gamma. So you can find here. The black line is the NFW profile, and for this is the blue and the right line is the corresponding dark matter spike profile, and it's around 10 to 12 order larger than the dark matter spike density is 10 order larger than, at least 10 order larger than the FW profile. So, but the dark matter spike is a theoretical hypothetical object. Whether there is a dark matter spike exists around supermassive black hole, we don't know. But recently, there is a very interesting study on such a supermassive binary system. It's so-called OJ287 system. For this OJ287 system, is a supermassive black hole binary with a primary black hole around mass around 10 to 10 solar mass and secondary around 10 to 8 solar mass. And we observe their orbital and their orbital decay rate. And we find that this orbital decay rate is larger than the orbital decay rate predicted from the gravitational wave. So that means there must be some other energy dispersion channel to make this supermassive black hole binary system to shrinkage. So recently there is this kind of study on the OJ287 system, and shows that such a orbital decay rate can be explained by the existence of a dark matter spike. And their study said the OJ287 system orbital decay rate indicate there is a dark matter spike with a power index 2.333, this kind of value. So this study is very interesting, but it's just an indirect evidence to show the dark matter spike. But such a orbital decay rate can be also explained by some other phenomenology. So, but still, this study is very interesting. So if dark matter spike really exists, so the primordial black hole in the dark matter spike and their corresponding merge rate will be enhanced. So let's see how the merge rate will be enhanced by the spike. So let's first introduce the primordial black hole binaries. There are two kinds of primordial black hole binaries. One kind is so-called early PBH binary. The early PBH binary is when PBH was formed at a very early universe. There were two PBH, and they just follow the cosmic expansion, follow the Hubble flow. They just escape away from each other. However, just for the Hubble flow. However, since the gravitational attraction between them will keep attracting them, and will cause they derive from the Hubble and cause them escape from the Hubble flow and to form a bounded state. And this is the so-called early PBH boundary. And there is already a lot of study on the PBH early PBH boundary merge rate, and their merge rate can be estimated by this formula. So this is so-called early PBH boundary, and there is another PBH boundary, so-called later PBH boundary. That is, when the structure start to form, when dark matter start to collapse to a dark matter halo, and the dark matter is located inside the dark matter inside dark matter halo has a very large density. Therefore, the number density of PBH inside dark matter halo will be increased. So when one PBH is in such a dark matter dense range pass by another PBH, so when their separation is very close to each other, they will emit very strong gravitational wave emission and lose their orbital energy. And this energy loss will cause they form a bonded system. So this kind of PBH boundary will form. This is so-called later PBH boundary. And in such a process, since the time scale for this two PBH boundary to form a boundary is very long compared with their merged time scale. So therefore, we usually use this two PBH capture rate as approximation as a PBH merge rate. So this kind of later PBH capture rate can be calculated as use the PBH number density times their capture cross section and their relative velocity of 2PH to calculate this capture rate and to as a approximation of the merge rate. So this is the two kind of PBH boundaries. So now what we want to study is if PBH located inside the dark matter spike, how the dark matter spike enhanced the later PBH boundary formation, later PBH boundary merge rate. So this plot shows the PBH merge rate for the early PBH boundaries, and you can find if the the PBH abundance in dark matter is 1, that means all the dark matter is PBH. So if it's 1, so for example, for 30 solar mass PBH, the corresponding PBH merge rate at current universe is around 10 to 5 per GPC volume per year. And this study studied the PBH merge rate in the dark matter spike. And if when they choose the PBH equal 1 and choose this gamma index equal 2, and its corresponding merge rate is around 10 to 6 per GPC volume per year. So this merge rate is comparable. The later PBH merge rate in dark matter spike is comparable to the merge rate of early PBH. Therefore, if the dark matter spike really exists, the PBH merge rate will be enhanced and modify its historical evolution. So let's first study how to detailed calculate the PBH merge rate in dark matter spike. So we need to first to estimate the later PBH merge rate inside one spike. So how to calculate it is follow just to calculate its capture rate in dark matter spike. We use the PBH number density times the capture cross section and times the relatively velocity, and we integrate. We obtain a merge rate in one spike, and also for each dark matter halo, we have one supermassive black hole, and in around one supermassive black hole, we have a spike. But in our local universe, we have a number of dark matter halo. We have a lot of supermassive black hole. So we need to integrate the PBH merge rate in one spike over this over all the supermassive black hole. So we need to estimate this supermassive black hole distribution, number density distribution. So the supermassive number density distribution is corresponding with the dark matter halo number mass distribution, and we using the dark matter halo number distribution, we times a relation between the dark matter halo and its corresponding supermassive black hole. Then we can obtain such a supermassive black hole mass function, and this dark matter halo and supermassive black hole relation can be calculated using such a supermassive black hole and velocity dispersion relation to obtain it. So therefore, we obtain the PBH merged in one dark matter spike, and we integrate it over all the supermassive black hole. Then we can obtain this PBH merge rate induced by this dark matter spike in our local universe, this gamma. So we can estimate some quantity. For example, let's say IPBH equal 1, all the dark matter is PBH. And when this gamma, the dark matter power density profile power index gamma, when it's equal to, you can find the PBH merge rate in dark matter spike is around 10 to 6 per GPC volume per year. So this value is very huge. It's comparable to the early PBH merge rate at current universe. So therefore, they will significantly modify our measurement on PBH merge rate. So let's say I always say this such an enhancement on PBH merge rate, later PBH binary merge rate will modify their PBH merge rate redshift evolution. But what kind of redshift evolution? Here you can find we calculate this gamma at different redshift. Since at different redshift, the supermassive black hole mass function behaves differently. So therefore here you can find for each PBH, for each dark matter spike, they have if their dark matter spike power index gamma is different gamma, this different gamma will change the amplitude of this gamma. Will change the amplitude of the merge rate. So this PBH merge, this gamma determines the amplitude. And for the shape, you can find no matter which gamma it is, the shape is always looks similar. Therefore, the shape actually depends on the redshift evolution of supermassive black hole mass function. So let's say how such a dark matter spike existence modify the PBH merge rate evolution. So this black line is the early PBH binary merge rate. If we just ignore any later PBH binary merge rate, just considering the early PBH binary merge rate, and here we're considering the FPBH is 10 to minus 3. That means only 0.1% of dark matter is PBH. So here we also use, for example, 30 solar mass as an example to calculate. And this black line is just the 30 solar mass at PBH equal 10 to minus 3 early PBH binary merge rate evolution with redshift. And if we considering the existence of dark matter spike, you will find when we add the dark matter PBH merge rate inside dark matter spike and with different gamma index, you can find the total PBH merge rate at different redshift will behave significantly different from the early PBH binaries. Therefore, this is what we so-called the how the PBH merge rate will in the later universe or in the dark matter spike will modify its redshift evolution. So, and here you can find this kind the amplitude, as we said, the amplitude is depends by this gamma index. And if in the future we can observe that this amplitude, it will tell us what the gamma index is. This gamma index will tell us how the dark matter is distributed inside dark matter halo. What's the power index of dark matter spike, and the shape. Shape, as we said, it depends on the supermassive black hole mass function relation with the redshift, and supermassive black hole mass function with redshift is corresponding with the dark matter halo relation with redshift. And dark matter halo mass function with redshift will tell us how the structure form at different redshift. So here, let's detail see how this kind of shape will be influenced by the different parameter. For example, if we choose if we choose the PBH mass is a monochromatic mass distribution, for example, 3 solar mass, 10 solar mass, 30 solar mass, and 100 solar mass, you can find their modification, their merge rate relay evolution with redshift are significantly different. And the reason is actually the late PBH boundary merge rate is independent on the PBH mass, but the early PBH boundary merge rate is depends on PBH mass. So when we're considering small PBH, small mass PBH, the early PBH boundary merge rate will be increased. So this peak do not looks very clear. But for the heavier PBH, and this bumpy peak will be very significant. So this is how the PBH mass changes this profile, changes this evolution. And also for in general, we considering for PBH, we always think about the normal type distribution. For example, the 30 solar mass, 30 solar mass with a mass variation as 1 sigma 1. And we can also obtain similar behavior, merge rate behavior with redshift. And also, as a for the how the diamond halo form also will change this merge rate relation with redshift. For example, previously we just considering the spherical collapse, this kind of spherical collapse. However, if for the diamond halo, their formation is not spherical collapse, it's ellipsoidal collapse. And for ellipsoid collapse, this will change the diamond halo formation at different redshift. Therefore, for example, for the ellipsoid collapse, dark matter halo collapse, we use this kind of formation equation, and you can find the PBH merge rate behaves differently for different spherical collapse and ellipsoid collapse, and also. For example, if the dark matter is not the cold dark matter, the dark matter is the fuzzy dark matter, and for fuzzy dark matter, the dark matter halo mass function also different from the cold dark matter halo mass function. They have a modification on small scale. So therefore, here you can find the right line is the cold dark matter formation history induced the merge rate relation with redshift. And the orange and the blue line is the different fuzzy dark matter mass induced the halo formation history and their corresponding merge rate with the redshift. Therefore, just from this kind of PBH merge rate with redshift, they will tell us what is the formation history of our dark matter halo, and they will tell us such a dark matter halo formation history is corresponding with which kind of dark matter halo collapse, spherical or ellipsoid, or is corresponding with whether it's corresponding with cold dark matter halo or it's corresponding with fuzzy dark matter. Meanwhile, when we observe the PBH merge rate, we also have some astrophysical black hole merge rate that will add some noise in our observation. But actually, we can find, for example, the population 1, 2, 3 star, their merge rate is already well studied. However, for PBH merge rate, their merge rate depends on FPBH. By changing this FPBH, the PBH the astrophysical black hole merge rate may not be very important. Meanwhile, for astrophysical black hole, their mass distribution has a broadly distribution, for example, around 8 solar mass, and this population 3 star is very massive one. But for PBH mass distribution, they always localize at some specific mass. For example, here we use a 30 solar mass as an example. Here you can find, okay, the PBH, if we just focus on a very narrow mass band, for example, 30 solar mass, and we're only using the PBH merge rate in this 30 solar mass to do some statistic to study their redshift evolution, we can have a very clear peak in our observation. Then, however, actually, dark matter spike is not a very stable structure. The dark matter spike also involve. There are two kinds of evolution of dark matter spike will cause the dark matter spike profile change. One mechanism is called two-body relaxation. That is, since the PBH boundary have an angular momentum, the angular momentum will forbid PBH to get close enough. Therefore, the two-body relaxation, this kind of angular momentum, will forbidden the dark matter spike to have an extreme high density. This is one mechanism to decrease the dark matter spike density. Another mechanism is so-called loss cone refueling mechanism. This mechanism is the strong gravitational attraction of supermassive black hole will keep attracting the PBH inside this loss cone range and will keep increase the dark matter spike density. So these two mechanisms will change the dark matter spike evolution. So for example, theoretically, we have a dark matter spike like this black line. However, if we considering the two-body relaxation mechanism, the two-body relaxation will flatten the dark matter spike using this kind of equation. But here you can find if we decrease the IPBH, this will cause this two-body relaxation time scale is extremely long, longer than the age of universe. In such a case, the two-body relaxation may not be very important. So therefore, for example, if we're considering the FPBH is 10 to minus 8, you can find we still have some peak. But if we considering FPBH is 10 to minus 7, we have a small peak. But if we consider FPBH equal 10 to minus 3, we do not have peak due to such a two-body relaxation. However, we have another mechanism to increase the dark matter spike density, that is so-called loss cone refueling. That is the gravitational attraction from supermassive black hole will keep attracting the PBH inside around their surrounding and increase the PBH mass around the supermassive black hole. But this loss cone refueling is very complex and it need a lot of theoretical study and numerical study. For example, for different shape of the dark matter halo tracks as axis-symmetric or spherical dark matter halo shape, this kind of loss cone refueling rate are differently. Therefore, here we both considering the two-body relaxation and loss cone refueling effect we can find. Here we show that for IPBH equal 10 to minus 4. This blue line is we both considering the two-body relaxation and loose cone refueling. And the right line is without any loose cone refueling and two-body relaxation. You can find we still have a peak here. And using such a peak, we can study how the dark matter is distributed inside the dark matter halo, and use the shape of this merged evolution with redshift, we can know how the dark matter halo was formed, whether the dark matter halo is CDM, cold dark matter, or fuzzy dark matter, this kind of thing. So in principle, using the primordial black hole merge rate, for example, we use the primordial black hole merge rate, the early PBH merge rate, we can use it to probe our universe on the background level to study the Hubble expansion rate. And we studied the late PBH boundary around the supermassive black hole inside dark matter spike. Their merge rate evolution with the redshift, that this shape can help us to know how the structure was formed. So this is basically how we use the primordial black hole mergers as a cosmological probe. So that's all. Thank you.
Thanks, Yang, for this nice talk.
Yeah.
So, the participants, if you have any questions, you can please unmute and ask. Okay, so I had one question. So, in the
Mm.
second part, so
Mm.
in the dark matter you are talking about is something else. It is not the PPH, no?
Yeah, it's not PBH. Actually, in general calculation, for example, when we considering this dark matter spike calculation, we assume an NFW profile. Therefore, in general, dark matter is a cold dark matter. But in
Okay,
this, we assume the PBH is 0.1% of the dark matter.
okay.
Yeah.
I understand. Okay, and the enhancement of the rate due to the dark matter spike. What is
Mm.
the physical reason behind it? Because it is in a
Mm.
tensor medium. Means what is the why is it happening? The enhancement. I
Oh,
missed that, but probably.
okay. So the key point is, uh, for example, the PBH merged enhancement in dark matter spike is due to the dark matter density in dark matter spike is very high. So
Mhm.
therefore, you can find when in the late PBH bandwidth formation channel, when the dark matter density is very high, this will in dark matter density is very high, so PBH density is very high, so the number density of PBH is very high. So the increase of the number density will increase the capture rate. It will increase the merge rate.
Oh, okay, okay. So as it is a part of the dark matter itself, so the number density is actually high, and that is the reason behind the. Okay, okay,
Yes, yes, yeah.
okay.
Mm,
So it
mm.
is not due to that the black holes are accumulating dark matters and increasing
Yeah,
in
no,
mass
no,
or
no.
something like.
Yeah.
Okay, okay,
Mm,
okay, okay, okay. Thanks for the
mm.
clarification.
Thank you for your question. Yeah.
Uh, okay, so the participants, do you have any other questions?
Yes, I do have a few doubts.
Yes, yes,
Um,
please.
Thank you, Doctor, for a wonderful talk. I just had
Mm,
some trivial doubts. Can we
mm.
go to that slide where you talked about the arrow function?
Oh, aerophone.
I,
Uh,
I,
yeah, yeah.
yes, I just wanted to know why that if the theoretical distribution and the observed distribution, if they are not the same, then the arrow function will be positive. Why can't it be negative?
Because here we calculate difference and square it.
Oh yeah, sorry, I did
Yeah,
not see the square
yeah,
root.
yeah, yeah.
Thank you.
But
And
actually,
I mean, yeah, go on. Sorry.
yeah, actually, in this kind of mechanism, there is a very key important. As I said, of course, when n prime do not when we guess the PBH mass function do not equal physical mass function, this PT do not equal PO. But what I said is if PT equal PO, that means n prime equal NP. But is that possible when PT equal PO, n prime still do not equal NP? This is very interesting question. In our numerical work, we didn't find such a case happen. But theoretically, there must be a mathematical proof to prove when PT equal PO, n prime equal NP. So this is very interesting question.
The other one was the
Mm,
same actually. In the next slide,
mm.
when you showed that I mean, I think the next one.
Oh, next one. Uh, you mean video, right? You mean this one? Uh, yeah.
I'm very
Karthik,
sorry. There was a
Uh,
power cut. Yes.
yeah.
In the graph that you showed, where the arrow function to be less than 0.01 with
Oh, you mean this one? Sorry. Uh,
I think he's having some
yeah,
issues
yeah,
with
yeah,
his connection.
yeah.
um. Hello, am I
Yeah, yeah,
audible?
yeah. Yeah, now I can hear you. Yeah.
I'm very sorry.
No,
There
no, no,
seems to
no
be a power
problem.
cut.
Yeah, yeah.
Yes. So here, why does it deviate so much with like higher values there in the end? I just
You mean
wanted to know that.
this one is a little large, right?
Yes.
Actually, this is a, a very interesting question. Actually, you can find for this equation, this is observable. And
Yes.
for NP, okay, here what we need to do is to do a redshift integration. For example, let's integrate it for this. Here I write from 0 to infinity. Actually, in calculation, I integrate from 20 to 100. And for example, for here, mm, mm, let's say that let's considering the major PBH mass around the tensor mass. So for tensor mass here, for tensor mass, if tensor mass PBH is observed at at redshift 0. So observed redshift mass is 10. But if 10 solar mass PVH is observed at redshift 100, so corresponding redshift mass is 10 plus 1 times 100. So it's around 1000. So that means for this kind of PBH mass, they corresponding with a very huge, very broad redshift mass range. However, for this 50 solar mass, for example, if 50 solar mass, when we considering the 50 solar mass PBH at redshift 0, their redshift mass is 50. But if we observe them at redshift 100, the redshift mass is 5000. So here you can find. So for example, 5000 is around this kind of distribution. You can find here the probability is very, very low. Such a very, very low probability
Yes.
will cause there is a very, very weak constraint from the probability distribution on this very heavy, massive PBH. And however, for this TIMS PBH, there is a very broad redshift distribution to constrain it. So error is not very large. But for very massive PBH, the constraint is weak, so error is a little large.
Okay, I understand.
Yeah.
Thank you.
Yeah, thank you for your question. Yeah, this is actually a very important problem when I calculate it in numerical work.
Yes.
So, any more questions? Okay, if not, let's thank our speaker for this nice talk and for the explanations. So, can you please share the slide with us?
Of course, I will send it to you later. Yeah.
Okay, okay.
Yeah.
Thanks.
And also, yeah, thank you for your invitation. I also enjoy this seminar. Yeah, thank you.
Thanks.
See you.
Bye.